All right, so today we're going to do, so what did we do last time? Last time we did longest path. So today we'll do some more graph problems. Right, so the theme has been starting from SAT, but looking at problems that we don't necessarily have algorithms for, but we start finding weird conclusions like, okay, I don't know how to solve 3-SAT, but I do know that if I did solve it, I could solve Boolean formulas. That seems unlikely. Same with subset sum. I mean, we have this funny running times and numbers are small. But in general, it's actually hard to do subset sum because you can take a 3-SAT problem and encode it into your subset sum problem. Yeah. Um, Similar with longest path in a graph, at some level, it doesn't seem that much harder than shortest path in a graph. Just one word gets changed. Um, and yet, we're able to take a SAT problem and with that very clever ladder-like structure, encode it as a Hamiltonian path problem. Okay. Although it is notable if the graph is a DAG, you can solve the problem. There's no cycles, and somehow it becomes much easier. So I think at least one of your homework problems is forcing you to think about which regime is which. Okay. All right. So today our problem is independent set. Okay. So I give you an undirected graph, uh, and the vertices could have weights, but we can do unweighted today. Um, and so a set of vertices is independent if there's no edges between them. Okay, so if it's like a friendship graph, you want to choose a bunch of people that have no friendships among them. And the goal is to get the maximum number of vertices in your independent set. Okay. So there's an undirected graph, which I think we keep reusing. And the question is, what is the largest independent set in this graph? 5? Did anyone beat 5? Okay, there's your extra dot. Anyone beat 5? 6? 6? Okay, which ones should I circle for 6? Left? Okay, so I can't take these two. This one? This one? This one? Oh, oh no, you don't want that one? That one's okay? You want that one? Oh, so maybe you don't want that one? Okay, so you do want that one? Okay. Okay. So right now we know how to get 5. People still think we can get 6? Okay, one second. That's very hard for. Okay, which ones should I not? Should I get rid of that one? Take the middle one instead. Sorry, delicately erasing. So I take this one instead. I think I know what you're talking about. I could take this one. Yeah, still 5. Oh, okay. Well, we'll just settle with 5. Oh, that's wrong. Right. Okay, so we can get 5. No one knows if you can get 6. That's an open problem. Okay. All right, but yeah, at least you get a sense of the problem, right? And it's tricky. Okay. Good. I can also do a decision version of the problem where I give you the target number. Is there an independent set of size 5? Is there an independent set of size 6? That, of course, makes it a yes or no question. Okay, so besides looking at general graphs, part of the theme today is also going to be studying some special cases of graphs and seeing if that changes things. Okay? So one version will be what's called an interval graph, but that's represented by a bunch of intervals along the line. Yeah, like between 0 and 1 and zero point 0.5 and 2 or something. And so you think of each interval as a vertex, and you put an edge between two intervals if they're overlapping. Okay, so you're trying to find the maximum cardinality of non-overlapping intervals, or maybe there's weight, so it's maximum weight, right? So this will happen a lot when you're doing like scheduling problems where you have a bunch of jobs, certain time durations, and you want to choose like the most profitable subset that you can feasibly do. Okay. And then another type we'll look at is in trees. So it's a particularly nice kind of undirected graph, and you want to just find the maximum independent set or maximum weight independent set in the tree. Okay. All right, so, okay, our usual forced participation, which allows you to not participate. So who's not voting? Oh, so we have 3 problems, each of those settings, and then for each one, you can either say we're going to get an algorithm or it's going to turn out to be hard. Yeah. And you can also not vote. So who's not voting? Okay, you're all voting. All right, let's start with general graphs. Who think is going to turn out to be hard? Oh, okay. Everyone, which is everyone, almost everyone's here today. 1, 2, 3, 4, 5, 6, 8, 12, 11, 12, 13, 14. Okay, 14. Good. All right, and then what about intervals? Who thinks this will also be hard? 1, 2, 3, 4, 5. Did you vote yes? No? Okay. And then who thinks it'll turn out to have an algorithm? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. So there's some more belief in algorithms. Okay. And now what about trees, a special case of graphs? Who thinks it'll be hard? Oh, nobody. Nobody. Oh, you're thinking. Okay, we'll come back to you. And then who thinks there'll be a polynomial time algorithm for trees? Okay. You're still thinking? Hard? Okay. Okay. And this will fit your psychology theory of the numbers going down and up and stuff? Okay. All right. Huh? This, oh yeah. Did it go well? Okay. Okay, good. We're all very excited. Okay, so for undirected graphs, like all of you guessed or knew or asserted or whatever, we're going to try to show it's hard. Yeah. Oh, geez. Okay. And so we'll start from a 3-step problem. Yeah, and somehow we have to turn it into some kind of undirected graph. What did I just do? Okay. We have to turn it into some kind of undirected graph. And we should be able to feed that into a black box that solves independent set. And we might ask yes or no, is there an independent set of size k? And that yes or no answer should somehow translate back into yes or no, the formula is satisfiable. Okay. So that means we probably want to make an undirected graph, and we probably want to choose a value k to feed to the black box. All right, so okay, so I gave you some kind of three-sat formula. You want to make some kind of graph and some kind of cardinality, right? And you want the formula to be satisfiable, at least in the most straightforward way, ideally. The formula is satisfiable if and only if there's an independent set of some size. Yeah. Okay. So the question is, how do we do this? Or what are just some ideas to try to model this? Yeah. Okay. So okay, good. So first of all, independent state, we're taking things, and in SAT, you're setting variables. So maybe we can have like you're taking vertices. So maybe we can have a vertex for each literal, x1 or not x1, meaning I set x1 to be true or I set x1 to be false, right? X1 or not x1. And you know you can't choose both, right? So if you put an edge in between these two vertices, that should be good, right? Okay. Um, so I guess I think that's the first step. Um, yeah, so that's fine. But now the next thing is like, how do you deal with clauses? Okay, so let's say I have some clause like this. First, you want to convert it to ands. 7 ands. Okay, what are the 7 ands? Oh, okay, so x1, so like x1 and x2 and x3 bar. Oh, okay, so the 7 ways to make it satisfiable. Okay. Okay, so maybe I'll try to draw, okay, if I understand you right. So let's call this C or something, right? And then maybe for each possible way of making the clause happy, we'll make another auxiliary variable. So for C, like there might be one for like true, true, true or something, another one for true, true, false, another one for true, false, true or something. So you end up with like 7 of these because there's 7 ways to satisfy it. Okay. So for each clause, I'll make a bunch of auxiliary variables for each possible way to satisfy the clause. And I guess you're probably thinking you can only satisfy it in one of the ways. So let me connect all of these with edges. Okay. Missing a bunch of edges, but use your imagination. And then what? Okay, so if I set x1 to be true, then I should not be able to take any of the ones where the first one is false or something, right? So I would add an edge like this, something like this. And then for x1 bar, it's not a great picture. If I set x1 bar to be true, which say I set x1 to be false, then I shouldn't be able to take any of the things that require x1 to be true. Yeah. Okay. Okay. So that's not the thing I had prepared, but it might actually work. So we can try in our very small white space uh, to prove this. So the result then is that you have your formula with m clauses and n variables, and you go to this graph we made with 2n plus 7n vertices. Okay, so these are for the variables, and this is like ways to satisfy each clause. There's 7 ways. Okay, so if we want to prove this to work, we just need to go back and forth on the if and only if, right? So one question is, if f is satisfiable, then there should be oh, we also need to choose k. So yeah, I'll let you guys choose in just a moment. But for whatever that choice of k, we want to show if f is satisfiable, there's an independent set of that cardinality k or bigger. And if there's an independent set of size k, then f is satisfiable. And then that will get you both directions. So yes means yes, no means no. Okay. So first, what should be our choice of k? M plus n. So I think the thinking is that we should be taking one for each variable, either x1 or x1 bar. And we should choose one for each clause. Yeah, and you can see from construction, you can only take at most one from each clause because the 7 things from the clauses are connected to each other. And you can only choose one of for each variable because they're connected with each other. So that's also the maximum or a maximum or an upper bound, I mean. Okay, so m plus n. All right, so let's say f is satisfiable. Well, what would be our independent of size m plus n? Yeah. Yeah, okay. So for each variable, if the x1 is true, I'll take the x1 vertex. If x1 is false, I'll take the x1 bar vertex. Okay, so that I'll set the variable. And now for each clause, there was some way that you satisfy whatever your assignment was, maybe true, true, false, or false, false, true, or whatever for that clause, right? And you know that must have satisfied the clause, whatever those literals are, those 3 literals. So we must have made a vertex for that clause because we made a vertex for all the assignments that satisfy the clause, all 7 of them, right? So for the first clause, whatever your values are is giving some code, true, false, true, true, false, false. There's some thing for those variables that made the thing satisfied. And we know we made a vertex matching that combination because we made a vertex for every combination that satisfied the clause. Okay. And I think the only thing to make sure is that there's no conflicts between the clause vertices we take and the variable vertices we take. Right? 'Cause otherwise, we did find a way to take one vertex for each variable, one vertex for each clause. And now just to check this one last thing, we just need to point out that, in fact, I think this should be the only clause that you can, oh yeah, that you can take given your variables. But that clause vertex you picked, when you look at the conflicts to the variables, it should only be the opposite of the ones you picked. Well, the clauses are connected to each other. Yeah, now give you an independent set of size m. Oh, so our value of k is m plus n. So you have to take one, in this construction, we have 2n plus 7m vertices. The 2n are 2 for each variable. 7m is 7 for each clause. And then the 2 variables are connected to each other in the natural way. And the clauses within a clause are connected all together. And then we added these cross edges, like x1 will be connected to all the clause vertices that set x1 to be false. Because you shouldn't be able to set x1 to be true and then take that assignment for that clause. Yeah, the picture's not super accurate or precise, but yeah. So, okay, that gets us from our independent set to an n plus m size independent set. Sorry, it takes us from our satisfying formula to the independent set of appropriate cardinality. I kind of ran out of space to write it down cleanly. And conversely, suppose you had an independent set of size m plus n. it might be intuitive, but let's just go through the steps. How do we argue that we have a satisfying assignment? Yeah. Perfect. So I think that gets you set up right away, right? So because there's many possible ways potentially to take m plus n vertices, but first establish that you must have one from vertex from each variable and one vertex from each clause. Now it's much easier to talk about the rest, right? And so now you want to construct an assignment maybe. It's like, I guess you just read off your independent set, right? So for each xi, I'll take xi to be true. If I took vertex xi, I'll set xi to be false. I mean, this is all stuff that you already understand when you constructed it. You just need to go through the motions. So now you make clear what your assignment is based on the independent set. And then lastly, you just need to verify that your independent set satisfies the formula, right? So, okay, if I set if I set these three things, then you could say, well, I must have taken the corresponding clause because I would conflict with all the other, I mean, the corresponding clause vertex for that assignment of the three variables, because I conflict with everything else. There's an edge to everything else. And then that's okay. Yeah. So I think those are three things. One, establish a structure of independent set. Oh, I have one of each kind of thing. Two, read off the assignment, so it's clear what the assignment is. And then three, make clear that it is satisfying everything. So just kind of reinterpreting, rereading this stuff. Usually these proofs are boring if you get the construction right, and they can be enlightening if you get the construction wrong. Yeah. So it is a little dry sometimes, but okay. So I think that works. As far as I can tell, I think that works. Um, Given that since I've already drawn the pictures, I'll show you the other way to do it. But actually, this way might be more intuitive. Um, okay. So what's the idea? In the other version, just like you said, the literals correspond to vertices, but actually here we're going to do clauses that correspond to triangles in the following sense. So Uh, for every clause, I'll make a triangle over the three variables or three literals that are in it. Okay. And we'll do that for like every clause. So that might be another one. Okay. And then, uh, like here, I'll put an edge between A and A bar because you can't take both. So in this construction, the idea is to try to take one corner of every triangle, where each triangle represents a clause. Uh, so when you have something like this, you'd have to draw the conflicting edges across triangles, C and C bar, things like this. So look like this. M clauses go to M triangles. And then we don't need to do the proof because we already have a different one. But you'd want to show that F is satisfiable if and only if you're able to take one corner of every triangle. All right, good. So that's the other construction, but I rather like the one we did instead as well. I think that one also is quite intuitive. Okay, good, good. All right, sounds good. Any questions? All right, so that turned out to be hard. Now we're going to intervals. I think the score is 4 to 9 for intervals. Okay. All right, so we're going to do maximum weight independent set of intervals. So those numbers represent some kind of weights of these intervals, and I want to get the maximum weight set of uh, non-overlapping intervals. Okay. All right. Any ideas? Yeah. First endpoint. Okay. Okay, that cut right to the chase. So let me let me go through the the rhetorical points. So let's say you first did a natural thing of let's try to make a like a recursive algorithm for this, right? And you might first like write a recursive spec. Oh, you give me a family of intervals, I'll try to return the weight of the maximum weight independent subset, right? And so a straightforward implementation might be something like this. You give me a bunch of intervals. Well, first, if it's empty, then the weight is zero. What can I do? Otherwise, I'll try taking an interval, and I either take it or I don't. If I take it, I need to remove all the overlapping intervals, and then I can recurse on the remainder. If I don't take it, I just remove that interval out, and I recurse on everything else. Yeah, kind of straightforward week zero homework kind of thing. But of course, the running time wouldn't be great, right? Because you're just enumerating everything, so you get some 2 to the n. And so the question is how to make this faster. It's exactly what was suggested. Okay. So suppose we sorted the intervals by left endpoint. Okay. So now I'll refer to like I1 as the first interval by left endpoint, I2 as the second interval by left endpoint. And I guess here I'm instead of XY, I'm using A1, B1, A2, B2, things like that. Okay. All right. So good. So, but like by now it should be almost like a trigger, like, oh, you see a sequence, you're hoping to do something like dynamic programming, right? Because now things are ordered and you can actually try to process things in a structured fashion, right? You're not punching all these random holes like you were doing in that first naive implementation. Okay, so let's do that then. So let's do a recursive spec. I use MWIS for maximum weight independent set. So give me a parameter, give me a sentence. Don't give me a shrug. Okay, I think we have K here arbitrarily, but so maximally independent set of from K will maybe the maximally independent set starting from the kth interval onwards. Right now you see all your clear subproblems. Right, you're just looking at suffixes. Right, there's clearly only n subproblems. That's great. Um, good. Uh, good. So, how do we implement this? Yeah. Okay. So what should I write down? Uh, is the first index bigger than K with, I guess, AL needs to be bigger than BK. AL will be the left endpoint of the alpha interval, BK is less. Okay? I'm not W of IK plus one. Uh, yeah. And you want the better of the two, right? So put a max here. Yeah. Of course, we're missing a small thing. Okay. I'm gonna be even lazier. All right, zero of K is bigger than n. If I'm just out of intervals, I just write zero. Okay. Good. Uh, sounds good. Is that what I have? That's right. Okay, so now, uh, what's the running time? Okay, so how many problems are there? How many problems? All right, n problems. And how long does it take to solve each problem? Okay, so it does take a little work to find L. I mean, it's not clear from my pseudocode because, oh, let L be, but it actually takes some effort to find it. So at least if it's naive and you scan over everything, how long would it take? But maybe you can do better if binary search. But to do binary search, we need to do a little extra. That's right, but that requires. Oh, actually, they're already in order, aren't they? Okay, they're already sorted. Okay, we've already ordered it initially, so that's fine. So log n time for each one, right? And so that gives you something like n log n, right? Yeah. Can you do better? Peter thinks you can do better. If it's not pre-sorted, yeah. Once it's sorted, you could also like do a little like kind of crawling through the A's and B's list and figuring out everyone in one pass, kind of. But again, the pre-sorting is going to take you n log n time anyway, so it doesn't really matter. Okay, good. So this will take you n log n, and it's maybe the first example where you could have done a little bit extra to make it a little bit faster beyond just the usual breaking it down into subproblems. Actually, it turns out the convex common subsequence problem had a lot of room for doing this kind of thing. Although I don't think anyone did. Oh, 1%? Okay. Oh, really? Okay. Okay. Yeah, the most straightforward one's m cubed, n cubed. But then you could start plucking off, because if you know that like AI is equal to bj, then you don't need to list I and j in your. Sorry? Yeah, you only need from A or B because you know that they're matching letters, and then you can do some searching. And yeah, so but that was only a small part of the rubric. But when I was writing the solution, it's like, oh my, you can really go off the deep end here. Okay, good. So yeah, you can do binary search and you can do a little faster. Okay, good, good. All right, so that turned out to be polynomial time. In fact, we could do that in n log n time. But the moral though is what happened, right? We had this completely unstructured graph. Things were hard. If I impose some structure, right? So interval graphs are a subset of all possible graphs, right? It imposes a certain structure on the corresponding graph, then suddenly you can do independent set. In fact, we did the harder version. We did maximum weight independent set on interval graphs, whereas unweighted was hard enough on graphs. Okay, but the theme of today's class is like, oh, sometimes when the graph structure is simpler or more constrained, you can do something that you couldn't do in a fully general graph. Yeah. Um, is there is there a way to identify, yeah, how do you distinguish the hard graphs from the easy graphs? So I don't think there's a clear line. Of course, some are more general than others. Like trees are clearly well, everything is a special case of a graph. So and it can vary by problem. And it can vary in funny ways too. So I don't think there's a simple rule for it, but I definitely think in this class it doesn't get. I think you guys will pick up on some patterns quickly in this class. Interval problems will often be doable, not always. There's some scheduling problems that get hard. Um, yeah, or maybe something else that often occurs on scheduling is that you have multiple computers that you can allocate jobs to. So you're assigning the intervals to different machines, but on each machine they have to be disjoint. This will tend to be harder, for example. So there now we've kind of gone from one line to multiple lines. Suddenly it gets hard. So I don't know. It's a little tricky. Um, of course, they're backed by proofs. On one hand, you have an algorithm, or on the other hand, you have a reduction either to or from 3 set. No one knows. Um, yeah, but okay, good. All right, last one is trees. And here I think it was 1 to 13. Okay. All right, so we'll see. This could be a massive win for you. Okay. Um, good. All right. Oh yeah. Oh, okay. So yeah. Okay. So this slide is ideas. So you're imagining a rooted tree or something, right? And you have something like this, and all the odd levels will give you an independent set, and all the even levels will give you an independent set. Can you just compare the two? That was the suggestion. Any ideas about this? Yeah. Yeah, it could be an uneven tree. So I'm sure it's not that hard to think of an example. Uh, Something like this or something. So here it looks like you probably want to take these three and these three, which are from neighboring levels. Um, okay, well, what if I added weights to the graph? Weights to the vertices. Maximum weight set. Okay, but how? So I give you some kind of tree like this, right? Okay, so if I give you that tree, what do subtrees look like? Ah, okay. Right, so you want to do something uh like this. So you want to fix a root, let's say this one, okay? And then you want to do something like, see if I can do this. Uh, so you want to think of this as the root. So you want to rotate it something like this. That didn't work well. Something like this. Why didn't that work? Okay, we just try this one. Okay, something like this. What? No, this was supposed to go better. Okay, so you can start trying to root this thing. Yeah. And now it's a little more clear what subtrees start to look like. You have the root, and then you have the children, and then you have subtrees. So once you root the tree, then you have the subproblems, and that's really the key step. Okay. So sort of like how we need to sort the intervals to find the structure. In this case, we need to root the tree, and then we can have subproblems that start to make more sense. Okay. Good. So that's the basic idea. How do you root these subproblems? I mean, how do you create subproblems? Once you root the tree, then you have subtrees. The subtrees are subproblems. Okay. In general, if you're trying to identify subproblems, the prefix sub is super useful. So like subtrees, subsequences, like that. That's a reasonable heuristic. Okay, good. So first, then we need to implement this thing. Yeah. So, or we need to do recursive spec. So I wrote MWIS. So give me a variable, give me a sentence. Yeah. Yeah. So we'll root T. somewhere arbitrarily. Yeah. Okay, so I think you're already thinking ahead about the implementation. Well, let's try this first, and then we can add maybe. Okay, so if I wanted to implement this, okay, so you're at some vertex, and you're trying to get the maximum weight independent set of that subtree. So yeah. Yeah, I think we're doing weights all right, W of V. Okay. All right, what if V is not a leaf? Okay, so okay. So either you take V or you don't is what you're suggesting, right? If you don't take V, then it should be. So, oh, oops. Uh, so maybe child, is that how I spell it? Yeah. Child X of V, the maximum weight independent set V, um, X, and otherwise you take V and it'll look more like. Yeah, so I'm not sure if this is like kosher. Um, but at least for sake of discussion first, since you can't take the immediate children, you want to get the maximum weight independent set of something underneath. Okay. Um, okay, so setting aside then running time, because the running time of this sum over grandchildren is a little bit ambiguous. Okay. But right now there's a question of correctness. Okay. So does anyone want to argue why it works or why it doesn't work? Yeah. It might not work. That's like neither option. Well, of course, but is there a tree where it won't work? No, it doesn't. So it's not going to work on. Okay, so you think this algorithm won't work on this tree? Okay, so either it will take this vertex, and then it'll only look at these problems. It'll probably conclude with 4. Or it won't take this vertex, and it'll try to get the maximum weight independent set of each of the subtrees, right? So I'll do the 3 right ones first. It'll definitely take this, definitely take this, definitely take this. And then it'll try to get the maximum weight independent set of this subtree. Yeah. And if we assume by induction it does the smaller trees correctly, then it's going to get this. Yeah. It is true that this is not the implementation I think in my book. Maybe some of you have read. If that's throwing you off or something. Yeah. So actually, I think correctness is okay. Yeah. So they have a slightly different algorithm in mind, which we'll get to, I think, in a moment. But right now, we're just looking at this algorithm, which is written in my terrible handwriting up on the slides. So it's because at each problem, you get this choice. You can either include the root or not. So it is true that if you include the root, you're going to skip a level and go down, as if you're doing even odd, right? But if you don't include the root, then the subproblems, you're going to just try to get the maximum weight independent set starting from each subproblem, right? And in that subproblem, you're allowed to include the root or not. It's going to make another, I guess, decision dynamically. Whereas even odd is just going to automatically take the children because you didn't take the parent. So this algorithm, every time, no matter what you did before, is asking, should I take the root or not? So that gives you the possibility of not just doing even and odd. Sorry? Well, in this same problem here, if you don't take the root, because the root basically has lots of, every time you take a vertex, you kill everyone that you're touching. So like in that problem, if you kill the root, you're gonna kill those three. If you take the root, you kill those three leaves on the left. It's not worth it. Oh, well, if it's weighted, then you have different options, right? So if it's weighted, a leaf may have a small weight and its parent has higher weight. So if you didn't take the leaf, you could take the parent with greater weight instead. So when things are weighted, like greedy things don't necessarily work because that thing that looks good now doesn't take into account the future, the weight of the next thing. Okay. So one slightly ambiguous thing is like, okay, it's convenient in describing intuitively what the algorithm is, say, I sum over the grandchildren. But now the running time is not quite clear because you go down to the vertex and down again, down again, down again. Okay. So an alternative way to implement this uh, is like this. So we could, if we want to avoid this summation over grandchildren, which is not the end of the world, you could write something that goes down a couple things, and then you can argue that for each node, I only traverse the parent edge from a grandparent once when I do the grandparent problem. So it'll be okay, but it might be easier to implement the algorithm as follows. So the only reason we have grandchildren is because you have to skip the children, right? And so you can do some kind of like complicated loop where you go an extra step down the tree. Or you can just do this. So we're just going to add a flag saying whether or not you're allowed to use the root. So this one I call the exclude root. If that's set to be true, you're not allowed to use the root. So I want the maximally independent set that may or may not be allowed to use the root of the tree. Okay. So now I have two choices when I have a problem. Well, if I'm not allowed to choose the root, there's nothing I can do. I just do the maximally independent set over all the children. If I can use a root, then I can either use it or not. If I use it, then for all the children's subproblems, they're not allowed to take that root. I'm not allowed to take the child, so I'm not allowed to take the root of the child's subproblems. So I set exclude true root to be true. If I don't take the root of my current problem, then I'm allowed to take the root of the children's problems. So I'll set exclude root to be false. Okay, and this might be easier to implement because you don't have to worry about jumping two steps and things like this. So we just add a flag. Yeah, make the algorithm simpler. Same overall running time, I think. Certainly easier to analyze this running time because you only go down to the children edges. I guess we haven't done that. Oh, well, it's already on the slide. So probably should have erased it. But for each vertex, the running time is proportional to the number of children. That's just your loop. So you end up counting each vertex once. So you get ON. Okay, so trees are often also tractable, in particular because subtrees give you subproblems. All right, good. Any questions? Yeah. Exclude root equals true. So I think if you take the root, you set the value to be uh, you set the value to be true for the subproblems because true means I can't choose a root. But I think we're on the same page. Okay. All right. So we have a little time then for one more problem. That'll get us half the lecture ahead. Okay. So our last problem today is graph coloring. Okay. So I give you an undirected graph. And so in a proper coloring, you want to give the graph, the vertices colors so that no two adjacent vertices have the same color. Okay, so good. Um, so I can take this graph and say, what is the minimum number of colors needed to color the graph? Or I can ask, is the graph colorable in 3 colors or 4 colors and so forth? Yeah. All right, so let's take this graph. It's the minimum number of colors you need so that every pair of adjacent vertices will have different colors. Okay, 4. Why did you say 4? Oh, okay, so you already know that there's this complete graph, so they will require different colors. Okay, so let me just color those arbitrarily. And the question is, can you extend that out to get 4 everywhere else? Maybe I'll point, and you can tell me what color. What color should this be? Blue? Okay. What about this one? How about this one? You should only have one choice, from what I can tell. How about this one? And how about this one? Oh, that was a little suggestive. Huh? Okay. And how about this one? Okay, good. So that gave you a 4 coloring. And in this case, because there is I planted a click on 4 vertices, you know that's actually a minimum. But sometimes it's not so obvious. Okay. I guess I forgot to put a poll up, but we're going to try to show that this problem is hard. Maybe that's not so surprising. Actually, what's an obvious? Yeah, sorry. Uh, is it solved for register? Oh, okay, okay. Yeah, so what's one way to interpret graph coloring? So it is sort of like a resource allocation problem. Each vertex is assigned to a different color, which I'm guessing for compilers is taking some sort of location in code and assigning it to like a register, right? And then the edges represent that they can't be given the same resource kind of thing. Well, they might do heuristics all the time. It's also possible that compilers have very simple kind of, they almost look like interval graphs or something, right? Because you're just following the code. I'm not sure exactly what comes up. Oh, so all these problems we do that are hard, people are still quite interested in solving, including SAT. There's a whole big industry of SAT solvers that claim to be fairly successful. Although if they were really successful, they'd be able to crack passwords, which is right. But like, um, so yes, or k equals 2. How do you do k equals 2? It's 2 coloring. That's just figuring out the graph is bipartite. So actually, if you just run BFS and you kind of build out this tree, you just need to check if there's any, spurious edges between kind of odd and even distances. So that's not so hard either. So you can like greedily color and get a 2 coloring. Yeah. Okay, but we're going to show a 3 coloring, at least, getting some kind of guarantee. I have a polynomial time algorithm that can always 3 color or find a 3 color, decide if a graph is 3 colorable. That's going to be as hard as SAT. Okay, so yeah, people, I mean, by now, like in a machine learning era, I don't know if any guarantees mean anything, right? I'm sure everything there is improbably or unexplainably successful, right? So, okay, okay, but yeah, okay, does claim make sense? Problem make sense, etc. Okay, all right. So to try to show that this problem is hard, I'm going to introduce an intermediate problem called subset 3 coloring. Okay, so subset 3 coloring is like 3 coloring, except each vertex is only allowed a particular set of subset of the 3. Okay. So in this picture, like that vertex in the top left, it can only use color 2 or 3. It's not allowed to use color 1. That vertex in the top right can use color 1 or 2. By default, if a vertex isn't marked with a subset, then you can use any of the 3 colors. Okay. So for this one, the question is, actually, this might be hard to see. Yeah, can you do a subset 3 coloring of this graph? Huh? Oh, I guess there's no 4 coloring. There's no 3 coloring. Okay, so the answer is no, but not for the right reason. Okay. Uh, well, I could have done a 4 coloring, but you get the idea. Okay, good. And the reason I want to do this is because when I go from 3 set, so what are the pros and cons? Uh, when I go from subset 3 coloring to 3 coloring, we're gonna have to figure out how to get rid of the sets. That'll take a little effort. On the other hand, when we go from 3 sat to subset 3 coloring, the subsets give us like a little bit of a degree of freedom when we design that mapping, right? Because it's more expressive. We have a few more tools at our disposal. Okay, so good. So I guess first we'll try to go in this direction, from subset 3 coloring to 3 coloring, or rather, yeah, if you have a good algorithm for 3 coloring, you have a good algorithm for subset 3 coloring. The subset 3 coloring isn't actually that much, or 3 coloring isn't, whatever. Okay. Any ideas? Yeah. Okay. Yeah. So you have something like this. So what should I add? Okay. So one vertex for each color has 3 vertices, and maybe I want to think of this one as sort of corresponding to color 1, color 2, color 3. Okay. And like, where should I start drawing edges? So I'll connect 1 wherever 1 is not allowed, which in this case are 2 or 3, but I guess it could have been just 2 or just 3. And I should connect 2 to, yeah, the 1 and 3 one. And so this will get connected to the 1 and 2s. Something like this. Okay. Right. Um, so let's say I 3-color this graph, right, which is going to erase all of this auxiliary information. What prevents me from doing stuff like this? Okay. So if I add these 3 edges, then they have to be different colors. Okay, so that's the high level idea. I add these 3 vertices and I know they must have distinct colors. Okay. And if I do some 3 coloring of this graph, which you already know is impossible, uh, in this case, uh, so, you know, and it colors it red, blue, or green or something, right? But based on the colors up here, I'll just call that color 1, color 2, color 3. Okay. And then that'll give me my 3 color. Okay, good. So that is the idea. Yeah, so I mean, yeah, just keep in mind the black box won't see your subsets. So it looks something, it'll just see the graph, and then you interpret based on how it colored your color palette up at the top what the actual 1, 2, 3 designations are. Okay, good. Good. So that's that idea. Okay, good. So that's that resolves that. Uh looks like the same slide again. Okay. So now the remaining part is to figure out how to go from SAT to subset 3 coloring. Any ideas? Or any, like, doesn't have to be a whole solution, but just generating some ideas towards yeah, no, yeah, no, yeah. Okay, so there's 3 colors, but naturally 2 choices of colors might be true or false, and then we'll some ambiguous color 3. I'm going to write neither because it's something, but it's not one of those 2. Okay, so if the colors correspond to these values or non-value, I guess, then what would be like a way? What should vertices correspond to? So if I assign colors, assigning colors to vertices is like assigning values to the variables, right? So maybe each xi should have a variable. In fact, because it's subset, we can do more, right? Yeah, you can say, oh, you can only assign a true or false or something. Yeah. And now the tricky part is figuring out how to do the clauses. Right, so I think this part's not giving away much. Yeah, so we're going to name the colors true or false. Right, and then we're going to have uh, variables. In fact, well, it turns out it's going to be a little bit more convenient um, to have a vertex for each possible literal, for xi or not xi. So we'll have two vertices for each variable. And we'll connect them with an edge. Because if I set xi to be true, then not xi has to be false. But it'll be easier then to put the not xi variable or vertex into some kind of clause, so to speak. Okay. Like let's say I wanted to model even just 2 variables, xa or xi or not xj or something. Okay, I'll enumerate all 7 possibilities. Now, one tricky part is before we added edges between all 7 of them, we made a click, but then you're going to need 7 colors just to deal with that click. So maybe there's something there, but at least that's one immediate technical difficulty. Okay, so for a clause, you want to create one vertex. Okay. Um, Something like this. All three are false, then this one has to be true. Okay. On the other hand, what if like two of them are true? Oh wait, oh I got it wrong. Okay, so sorry, you connected it to the opposite. So if all three are true, then this has to be false or something, right? Oh wait, sorry, no. Yeah. If all three are true, then that implies this one has to be false. Okay. But if one of them is false or two of them is false, then you could make the root true. Yeah. So in this case, okay, so I guess the only thing that's tricky here, yeah, so maybe this is a chance to use the third color. So if you had, so okay, sorry, this is a little detailed. So my clause is xi or not xj or xk in this example. So what we've done is we've added an edge to the literal xi bar. So all the opposites from our clause. Uh, and an edge to clause xj because xj bar is in our thing, and something to xk because x, oh, it should be to xk bar, right? Oh no. Maybe this is better than whatever approach I had in mind. Okay, so these are all the opposite literals. The thinking being that if I assigned all of them to be true, so I assigned all the opposites to be true, which means the ones I'm really looking forward to are all false. Okay? Then this one has to be false. Well, it depends. We have to choose which colors you're allowed to put here. But maybe it's false or something, right? Uh, okay. But then if one of these are false, which means the formula is actually true, you should be allowed, the clause is actually true. You should be able to allow some kind of true like color. So maybe we can add the color N for neither. Oh, okay. But now one problem is that all three of them were false, which means, I mean, if the clause is not satisfied, which means all three of these got true, you can still put neither up there. It's a little tricky. So yeah, it's not clear what happens when you have a mixed thing down below, which takes true and false away. That forces you to put neither up there. But then you can use neither in other situations as well. So this is pretty close. I'm actually kind of hoping this would work, but right now we're a little stuck at that point. Yeah, you shouldn't be able to put neither there when they're all true. Might be a fix. So I don't think you want to connect the xi's to xj's and stuff because you don't want like, oh, I set xi to be true, so I can't set xj to be true or something. So tell me if this hack works. So maybe what I will do is I'll add an extra one, connect it like this. And this one can only take the values true and neither. So in this situation, uh, you have to put neither here because true is taken, and then you have to put false. So I've added an extra auxiliary thing to try to fix this. Okay, let's see if this works. Oh, they are connected by, but here we're using the subset part. So, okay, one of these, so each clause has sort of gone two variables, but one can only choose true or not true, and the other one can only choose false and neither. Sorry, true and neither and false and neither. Oh, it does break? Okay, so I'll put a false here. Oh, okay, so now you're screwed? Oh, okay, now you're screwed because you can't put anything there. Okay, all right. Yeah, yeah, okay, so I'm not sure if this is solvable. Okay, I was hoping that would work. All right, so in the interest of time, I'll tell you what you do. It's actually quite subtle. Um, I'll just draw the picture. So you're gonna end up making a gadget that looks like this. Okay, so you end up introducing like 6 auxiliary variables or vertices. But there's an easier way to understand what's going on. So you just try to make one gadget for an OR. Okay, so let's look at like uh, C is equal to A or B. Okay, you just try to make a gadget modeling this. And if that's true, then you can see this thing as like, oh, here's one OR combined with another OR. Okay, so that's the idea. So the claim is that in this gadget, in this smaller gadget, C is always equal to A or B. Or you can only set C to be true if it's equal to A or if A or B is true. Okay. So in particular, all you have to do is look at, okay, what happens if it's false, false? Can you set the top one to be true? Okay. Okay, so one of these has to be true and one of these has to be neither. You could swap them, but that means that you have to put false on top. But if you did have true in either one of them, then you could put false here and you have a neither and then true. Okay, so in this little gadget, you can only set the root to be true if both of those leaves are false. In this funny little gadget. So now when you start looking at this thing, we're just combining two of them, right? So, when you're looking at A or not A2 or A3, one of those things has to be true. So either A1 or not A2 is true. And then that'll get you a true leaf for your next OR gadget. Or A3 is true, and that's the leaf you need for your OR gadgets. Because you're trying to figure out how to set the root to be true. So the only way to color the root is if one of the 3 leaves is colored true. Yeah, but I was hoping that our idea would work because it's clearly a little simpler than this, but it works. If the coloring doesn't exist. Oh, that sounds like a good exercise to take home. That would be cool if it works, but it's over, so I'll let the most of the class go. We can keep discussing if you want. Okay. All right, so next class will be a fun one because we're going to try to tie a lot of stuff together. Um, it'll be our last kind of exclusively about hardness.